Hi everybody, this is my Calculus 1 Exam 2 Review Problems and Solutions video. I'm going to go through a bunch of problems about derivatives, differentiability, linearity, product rule, quotient rule, chain rule, all the derivatives you'd want to know, linear approximation, some basic applications to physics and to optimization, and some theorems like the mean value theorem. We're going to start with a bunch of true-false questions where I will briefly explain the answer in addition to saying what the answer is. So we start with number 1 here. The function f of x equals the absolute value of x is continuous for all x. True or false? You need to know some things here. You need to know in particular in this case what the graph of the absolute value function looks like. It looks like a v, like this. And that is certainly a continuous function everywhere. You can draw it without picking up your writing utensil. This is true. Number 2, the same function, the absolute value function, is differentiable for all x. That is false. It's got a corner in the graph at x equals 0. The absolute value of x fails to be differentiable at x equals 0. If I said it's differentiable on some other interval that did not contain 0, then I could say true. But since I'm saying for all x, it's false. It fails to be differentiable at one point. Number 3, if f is differentiable at a number x equals c, then f is also continuous at x equals c. That is a true fact. That's a theorem. Usually the way we use this is we use something called the contrapositive of this. If f is not continuous at c, it's not differentiable there. So if your graph happens to have, for example, a jump discontinuity at some value c, not only is it not continuous there, it is also not differentiable. But this is how the theorem is usually proved. Number 4, even though the graph of the cube root of x has a vertical tangent line at this point, the origin 0, 0, which it does. Let me go ahead and draw the graph. It looks about like this. It is the inverse function of the x cubed function. The graph is smooth and therefore f is differentiable at x equals 0. That is actually false. I mean, it's a little tricky because the graph still does look smooth, so to speak, because it doesn't have any corners in it. But there is a vertical tangent. At the origin, it turns out the tangent line, I didn't draw it perfectly, is actually vertical, infinite slope, and that's enough to say that f is not differentiable at x equals 0. Number 5, if f prime of x is less than 0 for all x in some interval, then f is a decreasing function over that interval. That's a theorem. That is true. It can be proved with the mean value theorem. True for number 5. Number 6, true or false? So far we're alternating true, false, true, false, true. What happens here? The function x cubed is strictly increasing for all x, therefore f prime of x is strictly positive for all x. That sounds true, but well, we are alternating. This one is false. I don't always alternate true, false, true, false, true, false. That one is false. Why? Well, just think about it. Its derivative is 3x squared. And if I plug in, for example, 0, and that is the important point to plug in, I get 3 times 0 squared. I get a derivative that's equal to 0, not strictly greater than 0. This is not strictly greater than itself. Okay, no number is strictly greater than itself. Therefore, the answer is false. So just because something sounds reasonable doesn't mean it's true, and that's a big theme that this exam tests to some degree. Number 7. If a function is continuous on a closed interval from a to b and differentiable on the open interval from a to b, then there's a number c between a and b, so that f of b minus f of a equals f prime of c times, in parentheses, b minus a. Wow, that sounds like a mouthful. This should feel familiar if you've done some theorems in calculus related to derivatives, in particular something called the mean value theorem. Has hypotheses that start in the same way as this true-false question. The conclusion of the mean value theorem looks a little different. It's that f prime of c equals f of b minus f of a divided by b minus a for some value c between a and b. But this equation, when a and b are different, which I'm assuming here, is equivalent to this one. They mean the same thing, just go from here to here by multiplying both sides by b minus a. Therefore, by the mean value theorem, this is true. Number 8, if f and g are two functions that are both continuous on a closed interval and differentiable in the open interval, so this sounds like the mean value theorem, but I've got two functions now. And if f of a is equal to g of a, and f prime of x is always less than or equal to g prime of x for all x in the interval, then you can conclude that the function f of x is less than or equal to g of x for all x in this closed interval. That is actually true. I didn't alternate this time. That's called the Racetrack Principle. If you imagine the functions f and g representing the position of, say, a horse, two horses, and this would say they start at the same spot at the same time. This would say horse f runs slower than horse g because its rate of change with respect to time, if I pretend x is time, is smaller than the rate of change, the velocity of the other horse, horse g. That means horse f is always behind horse g. This is true. Last true-false question. The function f of x equals x to the fourth has a critical point at x equals 0. That is true if you think about it. F prime of x is 4x cubed. And yes, that means f prime of 0 is 4 times 0 cubed is 0, and that does mean x equals 0 is a critical point. But the problem is saying this point is neither a local maximum nor a local minimum, since its second derivative there is 0. And that is true as well. The second derivative is 12x squared. And if you plug in 0, you get 0. So this is set up to make you think that, hey, it can't be a local min nor a local max because the second derivative test requires f double prime to be positive or negative. However, even though that's a sufficient condition to have either a min or a max, it's not a necessary condition. If you graph this function, you will see, well, if you think about it carefully, it does have a minimum at x equals 0. I mean, the graph is very close to the axis when x is close to 0, but yeah, the function is strictly positive when x is non-zero. Even though when x is close to 0, like say 10 to the negative 1, f of x would be 10 to the negative 4 is even closer to 0, it's still not equal to 0. There is a minimum at 0, and therefore this is false, okay? It does have a, in this case, local minimum at x equals 0. All right, on to a problem about taking derivatives. Find the derivative of this function. You do not need to simplify, so we're just practicing our rules. Linearity, the derivative of a sum is the sum of the derivatives. There are a bunch of additions here. We need to use the product rule, the quotient rule, the chain rule, and memorize derivatives. The derivative of e to the x is e to the x, but I got a 2x up there. That means I need the chain rule. The inside function is 2x, so I take the derivative of the outside function, plug in the inside function, 2x, and then multiply times the derivative of the inside function. That's the derivative of e to the 2x. Here I need the chain rule again. In fact, I need it twice because I've got a composition of 3 functions. The outermost function is the tangent function. Its derivative is secant squared. But then I need to plug in the inner function, cosine of 2x, into that. Then I need to take the derivative of cosine of 2x. That requires the chain rule again. Derivative of cosine is negative sine. So I get a negative sine of 2x. Then use the chain rule again, multiply by 2, the derivative of 2x. I'm going to run out of room here, I think, but, well, maybe I can squish it in. Yeah, just double check things. If I make a mistake, I'll put a note on the video. I'm looking over things just to double check them. It looks good. Okay, on to this one. Here I've got the product of 2 functions. I need the product rule, and with the derivative of the second function, I need the chain rule. I also could bring the 3 down in front, but I won't bother doing that. So the derivative of 5x squared is 10x. That's the derivative of the first function times the second function, ln of x cubed, plus the first function, 5x squared, times the derivative of ln of x cubed. With the chain rule, that's 1 over x cubed times 3x squared. Okay? You could simplify this by doing some cancellation. Don't, okay? You might make a mistake, and all I'm grading for my students is the answer that's not necessarily simplified. All right, I'll go down here to take the last derivative. I need the quotient rule here, or I could multiply arcsine of 5x by x to the negative 2 and use the product rule and chain rule instead, but I'll use the quotient rule. I think of this as the high function, and this is the low function, and I say the quotient rule as low x squared, that's the low function. D high means the derivative of the high function. The derivative of arcsine of x is 1 over square root of 1 minus x squared. But I've got a 5x in there, so I get 1 minus 5x quantity squared, which if you did simplify it would be a 1 minus 25x squared in there. That's low d high minus high arcsine of 5x. D low, the derivative of the bottom is 2x. Over the square of what's below, I need to square x squared to get x to the fourth. Okay, so just looking this over. Oh, I did make a mistake. I was looking it over to make sure I didn't make a mistake. I did make a mistake here. In differentiating arcsine of 5x, I forgot to multiply by an extra factor of 5 here with the chain rule, the derivative of the inside function 5x is 5. I don't think I made any other mistakes, so we'll just leave the answer like this. All right. Hopefully no mistakes. I do make plenty of mistakes, so I'm hoping I don't. All right. Let f of x equal x cubed plus 2x plus 1. Note that f of 2 is 13. That must be important. Otherwise, why would I note it? You could double check that. 2 cubed is 8, plus 2 times 2 is 8, plus 4 is 12, plus 1 is 13. Yes, this is true. Also note that f is invertible. You'll see it passes the horizontal line test. If you graph it, you can certainly go ahead and use your calculator to graph it, and you'll get a graph that looks about like this. And the intercept there is 1, and the point, well, this is not to scale. 213 is on the graph. Let's pretend that's the point 213. All right, part A. So you can see it's 1 to 1. It passes the horizontal line test. No horizontal line goes through it more than once. So the inverse function exists is the point. Part A is to find f inverse of 13. Right there. Well, you just reverse the inputs and outputs from the fact that f of 2 equals 13. That means that f inverse of 13 equals 2. Hey, that makes intuitive sense if you think about the fact that these graphs are reflections of each other across the line y equals x. The function and its inverse, the point 13, 2 has got to be on the graph as well, and this is not a very good drawing. Not to scale. It's not a very good drawing, okay? These are reflections across the line y equals x. The graph of the inverse function is going to look something about like, it's always tricky, about like this. Let's see. Yeah, something about like that. Okay, not a super great drawing, okay? But you get the basic idea. Part B is to find f inverse prime of 13, the slope of the tangent line here. Hopefully it makes sense, or you've learned that the slope here of this point reflected across this line y equals x is going to be the reciprocal of the slope here. That's the key insight you need, or memorized fact you need. Symbolically, we could write f inverse prime, the derivative of f inverse, even though I can't find a formula for f inverse, by the way, and that's part of the point of the problem, so you can still find this derivative even though you can't find a formula for f inverse, is the reciprocal 1 over f prime of not 13, but 2, which I could also think of the 2 there as being f inverse of 13 as far as the more general formula goes, but you can also just look at the picture. So we need to find f prime of 2, but that's pretty easy. F prime of x is 3x squared plus 2. So f prime of 2 is 3 times 2 squared is 3 times 4 is 12, plus 2 is 14. So the final answer here is 1/14. Okay, that's the final answer. The slope here is 14. The slope here is close to 0. It's the reciprocal of the other slope, 1/14. Not a very good picture. This is the last one on the first page. Suppose you're given that f of 2 equals 8, g of 2 equals 1, g of 8 equals 2, f prime of 2 equals -1, and g prime of 2 equals 3. Oh, I guess one more. G prime of 8 equals 3. Compute the following derivatives. Here's A, h prime if h is the product, b, h prime if h is the cube root of f of x, and c, h prime if h is the composition of g and f. So this is the product rule chain rule and chain rule in a more abstract setting. We don't have a formula for these functions. Let's go ahead and take these one by one. So part A, h prime of x, or let's go ahead and just plug in 2 right away. H prime of 2, the derivative of h at 2, think about the product rule, is going to be the derivative of the first function at 2 times the second function at 2. Thinking about the product rule, plus the first function evaluated at 2 times the derivative of the second function evaluated at 2. And based on the info that we're given, f prime of 2 is -1. G of 2, where is it? It's 1. F of 2 is 8. And g prime of 2 is 3. So this is -1 plus 24 is 23. And once again, I'm crossing my fingers, hoping I don't make a mistake in all this. Part B, h prime of 2 if h of x is the cube root of f of x, which is, of course, the same as f of x to the 1/3 power. This one was the product rule. This one's going to require the chain rule. The outside function is the cube root function, the 1/3 power, x to the 1/3 power. So I need to bring the 1/3 down, but plug in the inside function, the f of x here, at 2. Subtract 1, 1/3 minus 1 is -2/3, but then multiply times the derivative of the inside function. This is an f of 2 here. So we get 1/3, I'll write this as a fraction, 1/3, f of 2 is 8 to the positive 2/3 because I put it in the bottom. F prime of 2 is -1. 8 to the 2/3, you could use your calculator, but you could do it in your head. 8 to the 1/3 is the cube root of 8, which is 2. Square that, get 4. 1/3 times 4 is 1/12 times -1. Looks like the answer is -1/12, if I have not made a mistake. All right. Part C. Over there, h is g of f of x. So h prime of 2 in this case, think about the abstract form of the chain rule. G is the outside function. Take the derivative of the outside function, plug in the inside function, evaluated at 2, times the derivative of the inside function evaluated at 2. Again, f of 2 is 8. So we have g prime of 8. F prime of 2 is -1. G prime of 8 is 3. So we get 3 times -1 is -3. Okay? All right. That's the first page. On to the page 2. This is more about interpreting derivatives, although you do need to find it as well. The population at P of Minnesota, where I live, in millions of people at time t, years after the year 2000. I think when I wrote this problem, I did use actual data. It's approximated by this function right there. Based on this formula, find the estimated population in the year 2019 and also how fast it's changing in the year 2019, in other words, a derivative. But A is just a function value. If you don't mind me abusing notation, I want to evaluate this function at, well, 19 years after 2000. I want to find P of 19. Technically, this is not good notation because I'm using the dependent variable name for the function name, but it's not a real big deal. So we get 4.919 times e to the 0.00754 times 19 power. If you want to find 0.0754 times 19 first, you certainly can. 0.00754 times 19. It's 0.14326. I need to take e and raise it to that power. Looking for mistakes. No mistakes. I'm really worried I'm going to make a mistake here. And get that. And then times 4.919. So the estimate for the population would be 5.67 if you round it 7. It's probably too many significant digits, but don't worry about that. 5.677. The units are millions of people. This would be million people. Is it accurate? I don't know. You'd have to go look up the population of Minnesota back in 2019, which we are currently past. Part B, how fast is it changing? In other words, what's the rate of change? What's the derivative? What's P prime of 19? Or I could also write this with Leibniz notation as dp dt evaluated at t equals 19 would be an alternative way to write that. Well, I need to take the derivative of this before I plug in 19. I need to think of this as the inside function with a t there. The derivative of the inside function would be 0.00754, that constant. The 4.919 gets carried along, e to the 0.00754t, but now I'm going to plug in 19. So I did really two steps there. I took the derivative first, then I plugged in 19. I used the chain rule when I took the derivative. The 0.00754 times 4.919 turns out to be about 0.0371. And then, I guess we've already done that one, but I'll redo it just all at once here. E to the 0.00754 times 19 is a little bit bigger than 1. Yep, okay. Times the 0.0371. I'll put more decimal places in here. 0.8926. Looks like, if I'd not made a mistake, the answer is about 0.0428. What would the units be? It would be units of p per units of t. That would be million people per year. Million people per year would be the rate of change. It's not asked, but you could convert that to, say, hundreds of thousands of people or thousands of people. If you converted it to, for example, thousands of people, you'd want to move the decimal 3 spots to the right. You'd say 4.28, 3 spots, excuse me. 1, 2, 3, 42.8 thousand people per year would be your estimate for the rate of change. Again, is that accurate? You'd have to look it up. Okay, that wasn't asked for. This is fine as the answer. Number 14, the temperature H in degrees Celsius of a cup of hot coffee placed on a kitchen counter is given by a function whose formula is not given. I will tell you it's exponential decay toward the room temperature, where t is minutes since the coffee was put in on the counter. Using units, explain the meaning of the following statements in terms of coffee temperature. Part A, f of 5 equals 40. That would say after 5 minutes, the coffee is 40 degrees Celsius. That's what A means, the practical meaning of that. And B is the practical meaning of the derivative, the fact that f prime of 5 is negative 1.8. I could say after 5 minutes or at time 5, the rate of change of the temperature, because that's what a derivative is, with respect to time, is negative 1.8 degrees Celsius per minute, units of temperature per unit of time. Part C, use these values to approximate the value of f of 7. So this is part C, use a linear approximation. You could do it two ways. I like to think of it like a two-step process. The change in the temperature, delta H, is approximated by the derivative at the starting time, 5 minutes, times the change in time. The derivative is negative 1.8. The change in time as we go from time 5 minutes to time 7 minutes is 2 minutes. So you'd multiply this by 2 and you get negative 3.6. And therefore, 3 dots means therefore, f of 7 is approximately the temperature at time 5, which is 40, plus the change in H, which is negative, plus negative 3.6, which I could also write as 40 minus 3.6. And that would be, 36.4 degrees Celsius. Okay? So I did it as a two-step process. You could do it as a one-step process. You could write it as right away as f of 7 is approximately f of 5 plus f prime of 5 times delta t, which is 2. You could do it as a one approximate equation that way. Okay? And it is an approximation. Is it going to be too low of an approximation or too big. The actual graph of h versus t is going to be decreasing and concave up toward the room temperature. And this is a linear approximation with the derivative using a tangent line that's going to be below the actual graph of the heat as a function of time, temperature as a function of time, and therefore this estimate will be too small because the actual graph will be above the tangent line. Number 15. The height of a ball thrown up in the air is given by that equation in meters. Part A, find the average velocity between time 1 and time 3. Part B, use the fact that the derivative is this to determine the moment in time when the ball reaches the maximum height. That'll be when the velocity is 0. C, find the maximum height including units. Okay, the graph of this is going to look about like this. It will have some maximum height. Finding where the derivative equals 0 is a critical point, and it will be a maximum. This is going to be a quadratic function whose coefficient of t squared is negative. It's going to be a graph that's a parabola that's upside down. It will have a maximum. Anyway, part A, average velocity from time 1 to time 3 is f of 3 minus f of 1 divided by 3 minus 1. That's change in height divided by change in time. And that is, okay, we got to plug numbers in here. All right. Bit of a pain, but we'll do it here. Let's just do it as fast as we can. So I'm looking at this formula here. First, I'm plugging in 3, so I get negative 4.9 times 3 squared is 9, plus 78.4 times 3, plus 3. Hopefully no mistakes there. 194.1 is f of 3. F of 1, plug in 1, is going to be negative 4.9 times 1 squared plus 78.4 times 1 plus 3, 76.5. 3 minus 1 is 2. 194.1 minus 76.5 is 117.6 divided by 2 gives me 58.8 for your average velocity from time 1 to time 3. The units would be meters per second. Geometrically, it's going to be a slope of a secant line between 2 points in the graph, but I don't want to try to draw where that might be because I'm not sure yet where, if t equals 3 is past the maximum height point or not. There's the derivative. I gave it to my students, but you certainly should be able to find it on your own. To figure out where the maximum height occurs, I need to set the derivative v equal to 0. In other words, f prime of t equals 0. I'm setting that equal to 0. Solve for t. I get this equals 0 means t is going to be 78.4 divided by 9.8 seconds. 78.4 divided by 9.8 turns out to be 8 seconds. Okay, that is the time of the maximum height, so that is going to be this location, which means the secant line for the answer to part A is more like right over there somewhere. It looks like it's part of the graph, but I mean it to be straight, whereas the graph is concave down. So the secant line would be underneath it, but anyway. Part C, to find the actual maximum height, I need to take the t equals 8 seconds and plug it into f. And that will be the maximum height because f gives the height. So once again, plug into f. Negative 4.9 times 8 squared is 64, plus 78.4 times 8, plus 3. Looks like the maximum height is 316.6 meters. Is this likely to be accurate? Probably not. It's not taking air resistance into account, drag on the ball. So this is probably not super accurate, but based on the simplified model where gravity is the only force, it's your best approximation. This page goes a bit quicker, at least the first few problems here. I do have my Calc 1 students by exam 2 try to learn the idea of an indefinite integral, which is just an antiderivative, or antiderivative if you prefer. That's what this symbol means. Find the most general antiderivative of x squared with respect to x, and Well, thinking about reversing the power rule, the answer is 1/3 x cubed plus c. Why? Because the derivative of x cubed is 3x squared. Therefore, the derivative of 1/3 x cubed, the 1/3 by linearity just gets taken along for the ride, is 1/3 times 3x squared is just x squared. So this is a bit of trial and error in conjunction with the power rule. A little bit of experience doing this kind of thing. Don't forget the plus c. For the most general antiderivative, the c is a constant. The derivative of c is 0, so it doesn't affect the derivative. This is the answer. This one is another antiderivative. You need to do a little bit of guess and check here. The derivative of sine is cosine, and therefore the antiderivative of cosine of x is sine of x plus c. I got a 2x in there, so I need a sine of 2x instead, and to compensate for the 2, I also need to multiply by 1/2. And once again, checking this is a good idea. The derivative of 1/2 sine of 2x would be 1/2 cosine of 2x times 2 because of the chain rule, and then the 1/2 and the 2 would cancel to give you just cosine of 2x. And again, the c doesn't affect things. Its derivative is 0. So there's your most general antiderivative or indefinite integral for that problem. Part 18 is a basic differential equation problem, initial value problem. It's got an initial condition. This is so basic, it's like hardly even worth calling it a differential equation, because you can come up with much more complicated differential equations. But really what we're looking for here is just another way of thinking about an indefinite integral here initially. You're looking for a function whose derivative with respect to x is 1/1 plus x squared. That can be written as an indefinite integral instead. It really means the same thing. I'm looking for a function whose derivative is 1/1 plus x squared. The most general answer is an indefinite integral there. That'll be arctangent of x, or inverse tangent of x, and I forgot to mention that's equivalent on the first page, plus c. That is your general solution of the differential equation, but now I also have an initial condition. I need to solve for the c using the fact that I want y of 0 to equal 2. So when x is 0, I want y to be 2. 2 better be arctangent of 0 plus c. Arctangent of 0 is 0, and therefore c is 2, which is the initial condition. That's not always the case. You can get problems where c is not the same as the initial condition, but this implies that your unique solution of the initial value problem is the arctangent of x plus c, where c has to be 2 to make sure that y of 0 equals 2. Okay, there's that one. Number 9. F and g are differentiable for all x. Q of x is f of x divided by g of x. And I guess I didn't say it here, but I'm kind of implicitly assuming I'm not dividing by 0. Directions say, hard to see here, by writing q of x as f of x times, this is g of x to the -1 power. Sorry that it's hard to see there. That's a -1 power. Use the product rule, chain rule, and some algebra to derive the quotient rule, in the way it's usually written as low d high minus high d low over the square of what's below, like we talked about before. So q of x, let me rewrite it here, is f of x times g of x to the -1 power. That is the same as f of x divided by g of x. So at the most fundamental level, when I write it this way, it's a product. I need the product rule. First function's f of x. Its derivative is f prime of x. Second function is just, well, g of x to the -1 power. And then, so that's the derivative of the first function times the second function, plus the first function times the derivative of the second, g of x to the -1 power, which I need the chain rule for. Bring the -1 down, subtract 1 from the exponent, so I get g of x to the -2 power, then multiply times the derivative of the inside function, g prime of x. Doesn't look like the quotient rule yet, but now I need to do some algebra. I've done the product rule and chain rule. Write these things as fractions and get a common denominator of g of x quantity squared in the bottom. This part initially is f of x divided by g of x. but I want to get a common denominator of g of x quantity squared, so I better multiply the top and the bottom of this by g of x, making the bottom equal to g prime of x. Oops, and there's a prime here. And the top is f prime of x times g of x. See the minus sign there? That's a minus. We already have the correct denominator of g of x quantity squared. The numerator is f of x times g prime of x. And then we can subtract fractions now because I have a common denominator. And now I'll go ahead and do it as low d high minus high d low, d meaning derivative, over the square of what's below. And there's the way the quotient rule is usually written. Okay? Number 20. Mass on a spring. Suppose an object of mass m in kilograms is attached to a spring with spring constant k. It happens to have units of newtons per meter. Suppose there's no friction. That means you can come up with a differential equation that models the motion, and you can come up with formulas involving cosines and sines. I'm skipping all that and just saying the period is this multivariable calculus function of m and k. That is how long the mass takes to make one period, to go from where it started to over here to back again, back to where it started, with the same position and same velocity. The velocity can be positive or negative, so it's a little tricky that way. But anyway, that's the period. You're just trusting me on that. Part A. I teach a little bit of multivariable calculus in Calculus 1. Find the derivative of t with respect to k with partial derivative notation. The d's are kind of curvy, but I don't care if my students also write it with ordinary derivative notation. It's just notation. Don't worry about it. That's it, part A. Part B is to evidently use this fact to do what? To take the answer from part A and this linear approximation right here to estimate the period when m is 1 and k is 20.5. So k is increasing from 20 to 20.5. It's increasing by 0.5. Now, you could just use the original equation to figure it out here, but we're trying to use a linear approximation here. Anyway, let's do part A. Part A, the derivative of t with respect to k. It's easiest to look at this version of the formula. Treat m as a constant. That's what you do when you take the derivative of this with respect to k. If you were taking the derivative with respect to m, you'd treat k as a constant. So this is just a constant right there. Derivative with respect to k, I got to bring the negative 1/2 down in front. 2 times negative 1/2 times pi times m to the positive 1/2, but I need to also subtract 1 from the exponent of the k. Negative 1/2 minus 1 is negative 3/2. This, if you like, simplify. I guess I'm not requiring it, but it simplifies to negative pi times m to the 1/2, or square root of m, over k to the 3/2, which is the same as k square root of k. Either answer is okay. Part B, we're going to use this linear approximation, which is the same kind of linear approximation we used on the previous page, except with different notation for the derivative there. Delta t, the change in the period, capital T, is approximately the rate of change of the period with respect to k, evaluated at the starting value of m and k. M is 1, k is, the starting value is 20, times delta k. Delta k is 0.5. I'm letting the spring constant increase by 0.5. How? By using a new spring, okay? That's similar in how it's constructed to the old spring. This derivative needs to be found with this formula, plugging the numbers in. So this is negative pi square root of m is square root of 1 divided by k times square root of k, using the original k, not the new k, 20 times square root of 20, or 20 to the 3/2 power, times 0.5. That derivative, let's go ahead and find it. I'll put the negative sign on at the end. Negative pi, or pi times 1 divided by, I'll do it as 20 to the 1.5 power. Put the negative sign in there. This is approximately negative 0.035,124 times 0.5. Same as dividing by 2. It gives you about negative 0.01. Oh, let's go ahead and round it. I'll keep more decimal places, even though it's not a good idea because it's too many significant digits, but let's not worry about it. So we're trying to estimate the period when m is still 1, but k has increased to 20.5. That's going to be approximately f of 1 comma 20 plus delta t, delta capital T. F of 120 is this, 1.4. That's probably too many significant figures as well, 0.40496 plus delta t, which is this, which is minus 0.017562. Yeah, as the spring constant gets bigger, the spring is stiffer, the oscillation is faster, and that's going to make the period go down a little bit. So we're going to have, again, 1.40496 minus this. It's about, okay, let's round here, 1.39 seconds. Okay, I could use more decimal places. And this one was about 1.40 seconds. So the period only decreased by about 0.01 seconds, which is, barely noticeable. Measurable, but barely noticeable if you were just watching the mass go back and forth. Take a breath. Here we go. It's a very comprehensive exam here, exam questions. This is an implicit differentiation problem. This equation, it's got x cubed and y cubed and x squared times y squared, defines a curve in the plane that does include the point whose coordinates are 2, 1. You may want to double check that. You don't have to, but 2 cubed minus 1 cubed plus 2 squared times 1 squared is 8 minus 1 plus 4 is indeed 11. So yes, it is on that curve. If it did not equal 11, it would not be on the curve. But we want to ultimately find the slope of this curve at that point, and then the equation of the tangent line to the curve at that point, and then approximate a y coordinate on the curve when x changes a little bit. Yet another linear approximation. Being an implicit differentiation problem, we need to assume this equation defines y as a function of x near the point in question. Y is a function of x near the point in question, has coordinates 2, 1. It's possible this curve fails the vertical line test. It's possible that overall it's not a function of x. But near this point, probably it's a function of x if you just take a piece of the graph. It probably doesn't have a vertical tangent there. That's another thing to be aware of. It ultimately will be the fact that we're not dividing by 0 that will guarantee this by something called the implicit function theorem, but that's kind of an advanced theorem. So now what I do, because based on that assumption, I could even pretend y equals f of x, is I differentiate with respect to x, keeping in mind y is a function of x. And if you like, you could replace each of these y's here and here with an f of x if you like. And it might be easier for you that way if you do it that way, but it's not traditional to use f of x notation. So I'll just take it step by step. The derivative of x cubed with respect to x is 3x squared. The derivative of minus y cubed is not 0 with respect to x. It's not 0. It's not a constant. It's not minus 3y squared, but I'm going to go ahead and write that down anyway because it's something else, it's 3y squared times the derivative of y with respect to x. And that is the chain rule there. This is a dy dx here. That's the chain rule that I used. If you were using f of x notation, that negative y cubed would be negative f of x cubed, and the derivative with respect to x would be minus 3f of x squared times f prime of x. That's the chain rule. That's what I did here, except with different notation. With this term, I need not just the chain rule, but also the product rule. X squared is the first function, y squared is the second function, really, of x. Ultimately, I could write that as an f of x squared. Product rule says take the derivative of the first function, 2x, times the second function, plus the first function times the derivative of the second. It's not 2y, it's 2y dy dx. I need the chain rule again. Derivative of 11 is indeed 0. It is a true constant. You want to find the slope, so you want to find dy dx. There's two terms on the left that involve dy dx. Let me factor out the coefficients of dy dx. It's 2x squared y from this term, minus 3y squared from this term, times dy dx. Move the terms that do not involve dy dx to the other side. This term and this term gives minus 3x squared and minus 2xy squared. Now divide both sides by dy dx. Or excuse me, divide both sides by this. And I think I'll switch around the order of these so that I have positive signs up top. 3x squared plus 2xy squared divided by this where I multiply by negative 1. So I'd have a plus 3y squared minus 2x squared y. At the point in question, x equals 2, y equals 1, dy dx. Plug in x equals 2. 3 times 2 squared, and y equals 1 plus 2 times 1 squared over 3 times 1 squared minus 2 times 2 squared times 1. Looks like my answer is going to be negative here. That's a 12 plus 4 is 16 over negative, this is a 3, that's a 8. 3 minus 8 is negative 5. Yeah, okay, that's times 1 there. 3 minus 8 is negative 5. So 16 over negative 5, which is the same as negative 16 fifths, or negative 3.2 for the slope, if I have not made a mistake. Part B used the answer from Part A, the slope, to find the equation of the tangent line. At this point, easiest thing to do is write it in point slope form. All this was Part A, by the way. Y minus the second coordinate of the point in question equals the slope, negative 16 fifths, times x minus the x coordinate of the point in question. You can solve for y as a function of x. I mean, you could have done that right away as well. You don't have to write it this way. Negative 16 fifths x minus 2 plus 1. You could certainly distribute the negative 16 fifths through the parentheses, but this is good enough, and this is actually a little bit more ideal for doing Part C. In Part C, we're trying to approximate the point on the curve when x is 2.1, and it's easier to have it this way because you can see 2.1 minus 2 is just 0.1. Y on the curve is approximately, this is the equation of the tangent line exactly, but now we're using that to approximate the curve. So on the curve, and I'm not going to bother trying to draw the curve because it would be really hard. I don't know what it looks like. Negative 16 fifths is again negative 3.2. 2.1 minus 2 is 0.1 plus 1 gives 1 minus 0.32 is 0.68 is the approximate y coordinate on the curve when x is 1. Is it exactly on the curve? I'm sure it's not. 22 is an optimization problem, though it's not an applied optimization problem. That'll come on exam 3. F of x is this cubic. Part A, find the critical points of f, just their x coordinates. Part B, make a number line and use the first derivative test to classify local maxima or minima. Part C, confirm with the second derivative test. And part D, find the local max and local min values, emphasis on the word values, the y-coordinates of the critical points. So, pretty standard kind of thing to do here. Take the derivative. 3x squared plus 6x minus 24. I want to set the derivative equal to 0 and solve for x. I can use the quadratic formula right away or try to factor it. It does work out nice to factor out a 3 here right away. Like that. And yeah, you could use the quadratic formula, but I can also see that this is easily factorable. This is 3 times, in parentheses, it would be a little experimentation would have revealed it's x plus 4 times x minus 2. You could double check that by foiling. Set this equal to 0 and solve for x. Your critical points, thinking of those as being x coordinates, are where this is 0, negative 4, and 2. Critical points can also occur where derivatives are undefined, but that's not going to be the case here. Excuse me. Some books say the critical points are the x coordinates. That's how I learned it. Some books call the points on the graph where you have a local max or min, or maybe a point like x cubed at the origin. I guess for you, like that, as critical points, including their y coordinates. But here we're just after the x coordinates. Part B, make a number line. How do you use the first derivative test? To classify these things, you want to confirm the derivative changes sign in certain ways at the critical points negative 4 and 2 by just thinking about the sign of this derivative in each of these 3 intervals that these 2 numbers break the number line up into. So for example, if I imagine plugging in negative 5 over here, or any other number less than negative 4, you don't actually have to evaluate it, you just have to think about it here. Will it be positive or negative? 3 times negative 5 plus 4 is negative 1, but negative 5 minus 2 is negative 7. 2 negatives times a positive make a positive. F prime of negative 5 is positive. Plug in a number in here like 0 into f prime, you're going to get negative 24, that's negative. F prime of 3, plug in 3 for x. In both spots you get positives, and 3 again is still positive. This is positive. So f itself is changing from increasing to decreasing to increasing, and effectively that means the first derivative test tells you that you're going to have a local max at negative 4 and a local min at 2. The graph of f is going to go up, then down, then back up again. Local max at x equals negative 4. Local max are also called the relative maxes. A local min at x equals 2. Part C was to confirm this answer with the second derivative test. Take the second derivative, plug in these critical points, and see whether you get a positive or a negative number. The second derivative here, look at this formula, is going to be 6x plus 6. So at the negative 4 critical point, you get negative 24 plus 6 is negative. And also the fact that this is a nice function, the second derivative is continuous, will imply that the graph is concave down. I'm going to go ahead and write that. Concave down near x equals negative 4. So the graph over there looks like that. And that means it's going to be a local max. It's good to think about the extra step of thinking about it being concave down, because it's easy to get confused, and because this is negative you think it's going to be a local min, but no. It is a local max at x equals negative 4 because the graph is concave down. On the other hand, f double prime of 2 is positive, so it's concave up, concave down, and concave up near x equals 2. So there's a local min at x equals 2. So we're confirming the answer. The graph over here is concave up. There's an inflection point. We're not asked for that. There's an inflection point where the second derivative changes sign, which will be where this is 0, which is x equals -1, halfway between -4 and 2, is where the graph changes from concave down to concave up. Part D is to find the local max and min values. Local max value is f of -4, not f prime of -4, f of -4. So that'll be -4 cubed plus, I'm looking at this formula up here, plus 3 times -4 squared minus 24 times -4 plus 7. -4 cubed is -64. This is going to be 3 times +16 is +48. This is going to be plus 96 plus 7. That's the -16. Plus 96 is 80, plus 7 is 87 for the local max value, if I've not made a mistake. The local min value is the value of the function at 2. That'll be 2 cubed. Look again up here. 2 cubed plus 3 times 2 squared minus 24 times 2 plus 7. That'll be 8 plus 12 minus 48 plus 7. That's 20 minus 48 is -28 plus 7 is -21. I hope I didn't make a mistake there. I think that's right. When you're optimizing max or mins over closed intervals, which we're not doing here, you also need to check the value of the function at the endpoints. I'm saving that kind of problem for exam 3. That's optimization over closed interval. Next page. Approximating the fourth root of 85 here in 2 ways. I'm giving pretty detailed directions and even saying what answers are. Part 1 of Part A is to show work confirms the local linearization, essentially the equation of the tangent line, to f of x at a equals 81 is this, okay? Part 1 of Part A is that, well, L of x, the formula is f of a plus f prime of a times x minus a. That's the general formula for the local linearization, which again is a function whose graph is the tangent line to the graph of f at the given value of a, which is the given value of x. So this is f of 81 plus f prime of 81 minus, or times x minus 81. F of 81 is the fourth root of 81, which is certainly 3. F prime of 81, I need the derivative. F prime of x is 1/4 x to the -3/4. So when I plug in 81, I get 1/4 times 81 to the 3/4. That's a 3/4 there if you can't quite see it. 3/4 power. Fourth root of 81 is 3. If I cube that, I get 27. 27 times 4 is 108. So this is 1/108. And without bothering to rewrite it again, it does match this. My students, if I give you a problem like this, you should rewrite it again. For the sake of time, I'm not doing that. 2, use L of 85 to estimate f of 85, which is the fourth root of 85, to 5 places after the decimal. That's probably too many significant digits. I don't know why I did it that way. But anyway, fourth root of 85, because f of x is the fourth root of x, is f of 85. That's approximated by L of 85. And just plug into the formula. So you're going to get 3 plus 1/108 times 85 minus 81, which is 4. 4/108 is going to be 1/27th. So 3 and 1/27th is why I want to write it as a mixed number is the answer. 1/27th is that, add 3. 3.037, 5 decimal places will be 0.4. How close is it? Well, 81 to the 0.25 power is exactly, oh, I want 85, sorry. Thought that seemed funny. 85 to the 0.25 power is this, 3.03637 instead of 704 there. So not too far off. In fact, in part 3, we are estimating the error, which is the actual value minus the approximate value. Error, and that's fortunate, it goes in alphabetical order. Actual minus approximate. Actual AC comes in the dictionary before approximate AP. And I essentially, well, I've almost done the work here. E of 85, the error when x is 85 is the actual value minus the approximate value. Of course, the calculator is giving you an approximation as well. But this is going to be approximately 3.03637 minus 3.03704 from the approximation. And that's going to be a negative error. And that's okay. About negative 6.7 times 10 to the negative 4, which is going to be negative 0.00067. 3 zeros and a 7. To go from here to here, you have to move the decimal place to the left 4 spots. That's the error. It being negative just means your approximation is too big, because you're subtracting something bigger. The graph of the fourth root function when x is positive kind of looks like the square root function. It's concave down, and therefore the tangent line is above it, and the linear approximation is going to be too big, making the error negative. Continuing to approximate fourth root of 85, we're doing it by Newton's method. Telling you what to do here. That's the function we want to find the root of, which will definitely be the fourth root of 85. Use 3.1 as your initial guess. Note that fourth root of 85 is 0. Why did I note that? Okay, that's just to confirm that it's the root of f of x. Find x1, the approximation obtained using Newton's method, showing the details, and I even gave the formula here, though I should have put a parenthesis there. Okay. You know, I'm being generous giving formulas here, but you know, your teacher may not give you the formula, and I might not give my students the formula in the future, but I did here. So there's the function, there's the derivatives. So if I use this formula to find x1, it's going to be x0. I'm using the formula when n is 1. I could use it then when n is 2 and 3 and 4, etc., but I'm just using it when n is 1. Minus f of x0 divided by f prime of x0. Again, x0 is 3.1. So this is 3.1 minus f of 3.1 divided by f prime of 3.1. Let's go ahead and find those things over here. F of 3.1 is 3.1 to the 4th minus 85. 3.1. There's a quicker way to do this on the calculator, but I'm doing this. 3.1 to the 4th minus 85. That's 7.3521, and then f prime of 3.1 is 4 times 3.1 cubed, 119.164. So what I get here is 3.1 minus 7.3521 over 119.164. So that is going to give me about 3.0380 for the value of x1 as your next approximation to the root. It's not quite as close as the linear approximation was. I'm sure it would be better, though, after a second iteration. By the way, here's the way to do all this quickly. I could plug my initial guess into there first. Then I could use the a and s as the value of x0, the previous answer, and essentially type in this formula with a and s in terms of x0. So it's a and s, which is x0, minus f of x0. It's going to be this, which I'm going to type in as a and s to the 4th power. A and s stands for previous answer. Minus 85 divided by 4 times previous answer quantity cubed. Enter, that is the value I got here, 3.0383. If I keep hitting enter a few times, it settles down very quickly. Already x2 is actually correct to that many decimal places. And x3, x4, it's already settled down toward a more approximate root. If I raise this to the 4th power, the calculator does round it to 85. What's this problem? Huh? Infinitesimals? This is not a standard calculus problem. And I'm not always going to teach it to my students, but I like teaching it sometimes. Show the derivative of x squared is 2x by using something called infinitesimals. Well, now, if you don't know about infinitesimals, you might want to just skip to the next problem. Though I give directions here, start by letting dy be f of x plus dx minus f of x. I'm imagining changing x by an infinitesimally small amount. And I'm looking for the change in y here. dy is f of x plus dx minus f of x. The new value minus the old value, when x changes by an infinitesimally small amount dx. But wait a minute, what is an infinitesimally small amount? There's no such thing in the real number system, but we can pretend. This is what the creators of calculus like Leibniz did. The function's x squared, so I need to take x plus dx squared minus f of x is x squared. Simplify. And the instructions say to let dx squared, when I ultimately simplify it, equals 0, because this is a joke. If dx is infinitesimally small, if I square it, I call it unspeakably small. Okay? 10 to the negative 100 squared is 10 to the negative 200. Okay, but 10 to the negative 100 is actually huge compared to an infinitesimal number. FOIL this out, I get x squared plus 2x dx plus dx quantity squared minus x squared. The x squareds cancel, and you're left with dy equals this. But wait a minute, go ahead and replace the dx squared with 0, and you're left with dy equals 2x dx, and therefore now dividing both sides by dx gives me dy dx equals 2x. There's a fun derivation of the derivative of x squared to be 2x using infinitesimals. Okay, this is kind of a joke, okay? But it's a joke that gets you the right answer. LOL, laugh out loud. All right, next problem. This is the last page. Yay, I'm as excited as you are. But it's, wait, a couple proofs. Oh no. Well, if you practice these ahead of time, they won't be as hard as they seem here. I do say what the goal of this one is, to prove that the 4th root of 1 plus x is less than or equal to 1 plus x over 4 when x is greater than or equal to 0 using the racetrack principle. And I will get you started, okay? Proofs are arguments. They must be in complete sentences, but certainly formulas can be part of your sentences, and abbreviations is fine as well. The way to start a proof like this, to use the racetrack principle, which was a true-false question way back when at the beginning of this video on page 1. Let f and g be defined by these formulas, the 4th root of 1 plus x and 1 plus x over 4, the f and g horses from the racetrack principle. Note that these functions are both continuous and differentiable for all x greater than or equal to 0. Also note they start at the same place at the same time, the two horses. Next, differentiate f and g to get ... I started the proof. Now you finish it. How to finish it? And what's the intuition behind what's going on here? The intuition is, graphically speaking, if you graph f and g here, the fourth root of 1 plus x when x is greater than or equal to 0 has a graph that looks about like this. When x is negative, it looks like that. And 1 plus x over 4 is really the tangent line to this graph at x equals 0. And because the graph of f is concave down, the tangent line will be above it. Like that. The fact that these functions are equal when x equals 0 means at time 0, pretending x is time, the two horses start at the same spot, at position 1, right there. F of 0 and g of 0 are both 1. That's mentioned here. And then they represent positions of the horses as at time x increases and g is winning. F is always behind g because f has a derivative that's always smaller than g. That must be what we want to show here. Okay, so now I'm continuing the proof. To get what for the derivatives? The derivative of f, well, this is the same as 1 plus x to the 1/4 power. So we're going to bring down the 1/4, get 1 plus x to the 1/4 minus 1 is negative 3/4 power. Chain rule says multiply times the derivative of the inside, which is 1, which doesn't affect things. 1 over 4 times 1 plus x to the positive 3/4 if it's in the denominator. And g prime of x is a linear function of x. Its derivative is 1/4. What do we want to verify? We want to be able to invoke the racetrack principle. So I need to verify that, in fact, horse f always runs slower than horse g. I need to verify that the derivative here is always less than or equal to the derivative there. That looks hard, but it's actually easier than you might imagine. Since x is greater than or equal to 0, 1 plus x is greater than or equal to 0, or greater than or equal to 1, excuse me. That's a 1. And 1 plus x to the 3/4 is also, well, greater than or equal to 1 to the 3/4, which is 1. And therefore, 3 dots means therefore, f prime of x, which is this, is less than or equal to 1 over 4 times 1. If the bottom of the fraction is greater than or equal to 4 times 1, then when I take the reciprocal of the bottom to give me the fraction, it must be less than or equal to 1 over 4 times 1, which is 1/4, which is, hey, that's g prime of x. For all x greater than or equal to 0. Okay, so looks hard, but it's actually easier than it looks, but you need to know what to say. Therefore, by the racetrack principle, which I'll abbreviate RTP, f of x is less than or equal to g of x for all x greater than or equal to 0, but that means, because f of x is this and g of x is that, that means the inequality we want is true, i.e., which means, in other words, the fourth root of 1 plus x, which is what f of x is less than or equal to 1 plus x over 4, which is what g of x is for all x greater than or equal to 0. Okay, and we're done. QED, Latin for we're done. Praise the Lord. Yay. We're happy. The proof is done. Okay. Last problem, which is also a proof. And it starts off kind of sounding like a little bit like the mean value theorem. F and g are two functions, are continuous and differentiable. I'm going to go ahead and say for all x instead of over just an interval from a to b. And satisfy some other conditions. F of 0 is 1, g of 0 is 0, f prime equals g for all x, and g prime equals f for all x. Weird. You might want to think about what functions f and g might be here. They are actually moderately familiar functions related to the word hyperbolic, if you want to look it up. Use the chain rule and the constant function theorem. What does that say? I'll get to it. And the assumptions to prove h defined by this formula equals 1 for all x. This difference, f of x squared minus g of x squared, always equals 1. It's an identity. How do you get started? Let h be a function defined by that formula. Note that h is continuous and differentiable for all x because I'm assuming f and g are. Okay, that's an abstract assumption I'm making. By the chain rule, h prime of x equals, let's go ahead and start that here, h prime of x equals, I need to differentiate this difference using the chain rule and technically linearity of the derivative too, because of the minus sign. It's the derivative of the first, which I need the chain rule for, 2 times f of x to the first power times f prime of x, that's the inside function, minus the derivative of the second, 2 times g of x to the first times g prime of x. By our assumptions, in particular, these two facts here and here, they must be relevant. I need to use them. That's the big hint about where to go, is you got to use your assumptions. Replace f prime with g. Replace g prime with f. Hey, and those two are the same thing. This equals 0 for all x. So the derivative of this continuous and differentiable function h equals 0 for all x. H has got to be constant. Its derivative is always 0 over the entire real number line. That's the constant function theorem. It would imply by the constant function theorem, CFT, h of x is always constant. It equals c for all x and for some constant c. If you only use the constant function theorem, you can't say what c is. But we're trying to prove ultimately that c is 1. What have we not used? We have not used the function values at 0. Since h of 0 equals, what's the formula for h? It's here. F of 0 squared minus g of 0 squared, which by the assumptions is 1 squared minus 0 squared is 1 minus 0 is 1. C must be 1. C must be 1. That's just for extra emphasis. Therefore, h of x equals f of x squared minus g of x squared equals 1 for all x. It's important to emphasize the for all x. Okay? And we're done once again. QED. Praise the Lord. Smiley face. Mathematicians also sometimes put boxes or filled in boxes or slashes at ends of proofs just to celebrate that you're done. As a final comment, what are f and g? It's not required in the problem, but f of x is called the hyperbolic cosine function cosh x. What is that? By definition, it's e to the x plus e to the negative x over 2. And g of x is the hyperbolic sine function sinh x. Excuse me. E to the x minus e to the negative x over 2. Okay, if you don't know about those functions, it's fine, but if you do, that's just a point of interest. And thanks for watching.